Hello, welcome to General Physics 1, and in this lecture we will be talking about the fourth and last part of the topic concerning the motion of a system of particles. In this lecture, we will continue talking about collisions, where we will apply the principles that we have developed in the last lectures and we will employ these principles and formulae to solve the problems of collisions of two particles. We will first deal with two particle collisions in one dimension, and we will involve ourselves in solving the problem of elastic collision in one dimension. Then we will consider the problem of inelastic collision in one dimension. As a special case of the inelastic collisions, we will talk about a special category of collisions which are called completely inelastic collisions, and we will take the case of one dimension for simplicity. And then finally we will talk about collisions in two dimensions. By that we will finish this lecture. And now we will be considering the solution of the problem of one-dimensional elastic collision between two particles. In the previous lecture, we have taken into consideration the problem of collision between two particles, elastic collision between two particles moving along a straight line, a one-dimensional problem, before and after collision, moving on the same line, and that's the one-dimensional problem, and we called that straight line on which they move before and after the collision, we call it the x-axis. We have discussed the basic principles of that collision and the basic formulae that we can apply to this type of collision. Then we mentioned that the conservation of momentum of the system applies before and after the collision, and thus the total momentum after collision equals the total momentum of the two bodies, colliding bodies, before collision. Also in this case, we have the conservation of energy applies in this case because it is an elastic collision as we mentioned. Thus, we have two equations, one arising from the conservation of momentum, which is simply m1 times v1 initial plus m2 times v2 initial, that is the total momentum of the two particles before collision, equals m1 times v1 final plus m2 times v2 final, and that is the final momentum of the system of two particles. So this is the first equation. The second equation is from the conservation of energy, but as we mentioned, it is easier to use another equation instead of the conservation of energy, which is the equation that is relating the relative velocities of particle 1 relative to particle 2 before collision, and the relative velocity of particle 1 relative to particle 2 after collision. We noticed that from the combination of the conservation of linear momentum and the conservation of energy, we can combine these two equations in order to get the formula for the relative velocities, and we can use that formula instead of the second equation, which is the conservation of energy, because it's easier to use. Now, thus, we can use these two equations, which are particularly simple to use. M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final, conservation of momentum. And then the second equation is V1 initial minus V2 initial equals the negative of V1 final minus V2 final. We combine these two equations together. From the second equation, which is the relative velocities, we find what's the value of V2 final. V2 final is found in terms of V1 initial and V2 initial and V1 final. And in this case, we will be able to replace the value of V2 final in the first equation. And we will thus have an equation that contains only one unknown, which is V1 final. We can find it from this equation, and then after we find its value in terms of the known parameters of motion or quantities of motion, we can go back and substitute in any one of the two equations which contain both V1 final and V2 final, and then find the value for V2 final. If it turns out that any one of the velocities, V1 final or V2 final, if it turns out that it's negative, that means the object or that particle is moving in the negative x direction. If it's positive, that means it is going forward in the positive x direction. So this depends on the solution and what are the results. So this is basically a background of the solution of the problem and how we can go about it. And now let's consider this problem and go forward in solving it. If we are concerned with the solution of the problem and finding the final velocities of the two colliding bodies, which means that if first of all we have an elastic collision in one dimension for the two objects. We have an elastic collision. This is our problem in one dimension, elastic collision in one dimension. Secondly, we have in this collision problem, we have the mass of the first object and the mass of the second object are both known. And also, if we know the initial velocities of the projectile particle and the target particle, if we know all of these parameters, we are left with the final, then with the final velocities. The unknown quantities are thus only V1 final and V2 final. Those are the only quantities that remain to be determined. We assume that the system is closed and isolated, which means that no additional mass is added to the system. The mass is constant of the system. The mass of each particle is constant, and no mass leaves the system. So the mass of the system is conserved during the collision and after the collision. And the system is isolated in a sense that no external forces act on this system of colliding two particles. So this is the setting of our problem. This is the setting of our problem. As we mentioned, we have two unknowns, which are V1 in final and V2 final, the final velocities of the two particles after collision has taken place. Having two unknowns to solve for, or to evaluate, or to calculate, that means we need two equations. And as we just mentioned at the beginning of this lecture, these two equations can be, first of all, the conservation of momentum, which is always applicable in collisions. So the total momentum before collision is equal to the total momentum after collision. That's one equation, and it's linear in velocities and linear in masses, of course. And the second equation can be taken as the relative velocities. And we have to remember that this formula for the relative velocities applies in one specific case only, which is this case, the case of collision of two particles. The collision is completely elastic collision, where conservation of energy applies and conservation of momentum applies, of course, and the collision takes place in one dimension. So in this particular case, that formula applies, which is the formula for the relative velocities, as we have discussed before. So now we have these two equations, and as we mentioned a little while ago, we find the value of the velocity, the final velocity of the second particle, if V sub 2 final, in terms of V initial 1 and V initial 2, and in terms of V final 1. So if we substitute this value, V2 final, in the first equation, which is the equation for the conservation of momentum, we will have an equation that contains only one unknown variable, which is V1 final. We can solve these two equations thus and find the value for V1 final, and it is a simple algebraic exercise for you to do. If you make this substitution for V2 final and rearrange the terms, then you will find out that V1 final is equal to M1 minus M2 divided by M1 plus M2, all multiplied by V1 initial, plus 2M2 divided by M1 plus M2, all multiplied by V2 initial. This would be the final velocity of the projectile object after collision. Similarly, we can evaluate or find and determine the velocity, the final velocity of the second object, which is the target object, by introducing this value of V1 final, which we just evaluated. If we substitute its value in any one of the two equations that we are using, we can find the value for the final velocity of the second object, the target object, and it is found to be V2 final is equal to 2M1 divided by M1 plus M2, all multiplied by V1 initial, plus M2 minus M1 divided by M1 plus M2, all multiplied by V2 initial. Now, these two equations give the values for the final velocities of the two colliding objects after collision has taken place. Notice that these two values are given in terms of m1, m2, v1 initial, and v2 initial, all of which are known right from the beginning as initial conditions of the problem. Now we can take some special cases of this result in order to convince ourselves of how systematic and how logical is this result of the collision. Suppose that as a special case that we have a very massive object at rest that is struck by a relatively much smaller object that is moving with an initial velocity v1 initial. In this case, the mass m2 is much bigger than m1, and v2 initial is 0. Let's see what is the result. The logical result of such a collision would be that we should expect the projectile object to rebound, to go back after collision with exactly the same initial velocity, with its initial velocity, but in the opposite direction to its initial motion. Why? Because we have assumed that m2 is so large, like for example, a football striking earth. The second object is so massive that after impact it does not change its motion at all. If it's stationary, it stays stationary. So, and since the collision is assumed to be elastic, then we have a conservation of energy. That means the projectile object is coming to collide in a collision course with the massive object, and after impact it should rebound with the same velocity in order to make sure that the energy is conserved, that the kinetic energy is conserved. Let's see this. How does this happen? Now, if we apply this to v1 initial to see what's v1 final, to see what's v1 final after impact, what's the velocity of the projectile object after impact, what it is in this case, we have assumed that v2 initial is 0. That means the second term in this equation drops down. And in the first term, we have m2 is much larger than m1, in which case we can drop m1 relative to m2. So we have minus m2 over the line, and we have plus m2 under the line. Minus m2 over plus m2 is equal to minus 1. Thus, we obtain v1 final is equal to minus v1 initial, as expected. The final velocity of the object as it strikes a massive object is equal to its velocity, its initial velocity in magnitude, but in an opposite direction. The final velocity of the second object, the massive object, after it has been stricken by the smaller object, can be also evaluated in this special case. We have v2 initial is equal to 0, so the second term drops down in this case, and we will be left with the first term, which is 2m1 divided by m1 plus m2. Since m1 is so small relative to m2, or m2 is infinitely larger, as we assumed, relative to larger than m1, we can drop m1 from downstairs and we will have 2m1 over m2. m1 over m2 approaches 0 because m1 is so much smaller than m2, and thus v2 final approaches 0, which is the case that we encounter when we have a small object striking a very large and massive object. Thus, we realize that this result that we have obtained is systematic, and it's somehow logical. We are somehow having confidence of the correctness of this equation, and we are having some sort of a sense of the applicability of this equation. As a second example, let's flip our example the other way around. Let's assume that the massive object is moving with an initial velocity is m1. Suppose that m1 is the massive object and moving with v1 initial, where m2 is a small object and relatively much smaller than m1, and is stationary with v2 initials equal to 0. Then let's take into consideration this particular example and try to think for yourself, what do you expect to have if a very massive object having an initial velocity strikes a smaller object which is stationary? What do you expect to be the outcome of this collision? And try to plug in the values and make the right approximations, meaning taking m2 to be very much smaller than m1, and do the right approximations and obtain values for the final velocities of the first object and the second object in this case. Try to think of this problem and check out your understanding of the formula and of your understanding of the outcome of an elastic collision. One of the questions that might arise as we are dealing with the problem of collision in one dimension is, what is the center of mass velocity? Some lectures ago, few lectures ago, when we were discussing the motion of a system of particles, we mentioned that if we drive a cue ball in a billiard game towards a stationary target ball, then we expect that the outcome of the collision, the two particles, the two balls, would continue to move forward after collision. And we mentioned then that a particular point, which is the center of mass of the two balls, which lies in the middle between the two, midpoint between the two balls, because they have the same mass and they are identical balls. This particular point, which is the center of mass, is the one that moves exactly in the same fashion before and after collision, as if the collision has never happened. So we have mentioned that before, and after we have developed the means to calculate the final velocities after collision has taken place, now we have the tools to check that statement numerically. So we ask ourselves at this point, what is the center of mass velocity if that particular point is moving with a given velocity? What is that velocity before collision and after collision? we can evaluate the center of mass velocity before the collision very simply, because we can use the formula which says the total linear momentum of the system consisting of the two colliding particles is equal to the total mass of that system, which is m1 plus m2, multiplied by the center of by the velocity of the center of mass of that system. So P is equal to m1 plus m2 times v center of mass, from which we can obtain the value v center of mass is equal to the momentum of the system divided by m1 plus m2. Now, which momentum shall we take into consideration? The answer is simple. It doesn't matter, because we have discussed this problem before, and we have mentioned clearly that collisions do conserve momentum. And we have seen this in different occasions, and we have derived it, and we have talked about it in different occasions. Momentum is conserved before and after collision, which means it doesn't matter which P to take, whether it's P initial before collision or P final after collision. So, but because we know the initial velocities of the two objects before collision, so it would be very much easier and straightforward to find the velocity of the center of mass before collision. So before collision, the velocity of the center of mass is simply the total momentum, which is m1 v1 initial plus m2 v2 initial over m1 plus m2. This is the velocity of the center of mass as evaluated from the initial conditions, from the initial moment. But again, it does not matter if we consider the final state of motion of the system, since, as we mentioned, this system is isolated and closed. It doesn't have any external forces acting on it, and thus the momentum is conserved after collision. Thus, if we take into consideration, instead of P initial, if we take P final, we will be arriving at exactly the same answer. So I motivate you to go ahead and show that this answer that we just obtained is exactly the same answer if we consider V1 final and V2 final instead of considering V1 initial and V2 initial. Meaning, if we take the center of mass velocity after collision, taking the final momentum, linear momentum of the system after collision has taken place, and using the values V1 initial, V1 final, and V2 final that we have just calculated a minute ago, if we use these velocities and multiply m1 v1 final, which we just found, plus m2 v2 final, and divide that all by m1 plus m2, we'll obtain another result for v center of mass. And you should convince yourself, after doing some algebra and rearranging the terms together, that this result is exactly the same as the result that we have obtained by using the initial momentum of the system. This is a good exercise to do in order to make sure that we understand the conservation of momentum during the collision. Now we are at a point where we can discuss the problem of an inelastic collision. We have mentioned that collisions are either elastic or inelastic. So now we take the problem of an inelastic collision and we take the one-dimensional case as a special case. But as we have talked before, since momentum is a vector quantity, the same principles that we develop for a one-dimensional case can be applied for more than one dimension, and that will be discussed at the end of this lecture. So let's take into consideration the one-dimensional case. In this case of an inelastic collision, energy is not conserved because the collision is not elastic. However, we should remember that the momentum is conserved. The momentum is conserved. It's conserved in all collisions. Now, a special case of inelastic collisions, a special case is what we call the completely inelastic collision. The completely inelastic collision is a special type of inelastic collisions where the particles, after they collide, they do not separate after collision, but rather once they collide, they stick together and they keep moving with the same final velocity. That when two particles collide, stick together and keep moving together, that is called a completely inelastic collision. Two colliding cars, for example, or a car with a truck, where both of them they keep sliding together across the street, is an example of the completely inelastic collision. The completely inelastic collision is, for example, when you have a meteorite striking Earth, the meteorite sticks to the crust of Earth, and supposedly just because the Earth is so massive, we don't feel the strike. But in fact, this is an example of the completely inelastic collision where the two objects after strike, they are stuck together, and the kinetic energy of the system is transformed into some other form of energy, as we see in the background of this picture. If we imagine the meteorite hitting the Earth or hitting the surface of the Moon, for example, because in an inelastic collision we lose energy, and this energy goes into different forms of energy in nature. So in the problem of a completely inelastic collision in one dimension, we have one object with mass m1 moving along the x-axis with velocity v1, and we have a target object m2 moving along the x-axis also with velocity v2. This is the one-dimensional case where after collision the two particles stick together, and we have resulting one object of a certain shape. It's different than the initial shapes of the two colliding objects, and the mass of the resulting object after the two have stuck together is simply m1 plus m2, and that one combined object moves with a final velocity after collision, which we call capital V. So capital V is the final velocity of the combined objects after collision, and the motion is along the x-axis. This is a one-dimensional collision which is completely inelastic, in which after collision the two particles are stuck together. So what do we have in a completely inelastic collisions? The two particles are stuck together and move with a final velocity that is equal to capital V. And we have in this collision conservation of momentum is applied, because as we mentioned, conservation of momentum is always applied to any collision of any type, of any form. But we do not have conservation of energy. We do not have conservation of energy. Thus, we have one equation only, which is coming from the conservation of momentum, and that says that the initial momentum of the system, which is simply the momentum of the first object m1 v1 plus the momentum of the second object m2 v2, is equal to the final momentum, and the final momentum is the momentum of one combined object which has a mass m1 plus m2, and the final velocity of it is v capital. So we have this very simple equation which involves only one unknown, which is v final of the combined object after impact, after the collision has taken place. If we know the initial velocities, then we can determine the final velocity. At any rate, it is not necessary to ask ourselves to know the initial velocities and to ask ourselves what is the final velocity. Sometimes we are interested in determining the initial velocity of a given object, but we don't have the tools to measure it. So we use this problem of completely inelastic collision to determine the velocity of that object. For example, we cannot measure, it's difficult to measure the velocity of a bullet going out of a gun, leaving a gun. It's difficult. But if we arrange a special setup, we can measure that velocity. For example, we can bring a big block of wood to make sure that the bullet does not penetrate through. And we can hang that block from the ceiling with a rope of known length, for example. And then we can shoot the bullet at the block of wood. And after the impact, the bullet comes to rest inside the wooden block, and this collision is completely inelastic because the two objects stick together and they travel after impact together with the same velocity, which is capital V. Now, the velocity of the block with the bullet inside, the velocity is particularly small somehow, and we can measure it. We can measure it by one way or the other. Actually, we can measure it by considering the conservation of mechanical energy, because right after impact we have a kinetic energy only for the system consisting of the block and the bullet inside, and then this kinetic energy is transformed into potential energy as the system rises up. So if we calculate how high does the system rise to, and we figure out what is the potential energy, which is m, the total m of the system, times g times h, that's the potential energy that is increased, and this is equal to the kinetic energy by which the system was moving right after impact. So we have a means of determining the final velocity, which is capital V of the system after impact, and this will give us a simple method of determining what is the initial velocity of the bullet. That's a particularly good example for the usage of this type of collision between two objects. checkpoint, as a checkpoint, just evaluate the kinetic energy of the system of two objects before collision, evaluate the kinetic energy of the system after collision, after the completely inelastic collision, and find the difference in kinetic energy between the kinetic energy after collision and before collision. There is a difference. There is a waste in energy. The kinetic energy has decreased due to this collision. Try to find this difference and try to explain where did this kinetic energy go? Where did this change in kinetic energy go? The loss of energy, where did it go? Now we are at a point of considering collisions in two dimensions, and as we mentioned, collisions in two dimensions are just generalizations of collisions in one dimension, where we can take into consideration for example, two components of the momentum, and apply the momentum conservation in two directions instead of in one, thus obtaining two equations. Or in general, if we have three-dimensional motion, we can apply the conservation of momentum in three dimensions. Thus we have three equations. If we consider a glancing collision, just touching between two objects, one of them is of mass m1, moving with velocity v1 initial, as a vector, because we are considering the motion in three-dimensional space in general, but we are reducing the problem into two-dimensional. And a target object of mass m2 at rest. We consider this problem after the two objects collide. We assume that the two objects fly off with an angle θ1 and θ2 respectively after collision, and here we take the x-axis along the initial direction of the velocity v1 initial. Just for simplicity, this will simplify the analysis of the problem, but it doesn't matter even if we choose the x-axis in a different direction. As far as we take into consideration the right components, we are fine. And this is the problem of the glancing collision. As we mentioned, m1 is striking with v1 initial, is striking m2 at rest, and then the two particles fly off with angles θ1 and v1 final, velocity v1 final, and θ2 with velocity v2 final after collision. And if we have an inelastic collision, then we have conservation of momentum applied, and this is the conservation of momentum in the x direction as we apply it. Notice that we have to analyze the finals into its two components, the x and y components, and this is the coming from the application of the conservation of momentum in the y direction. Notice that the momentum, the y component of the momentum of particle number 1 is downward, it's negative, and that of particle number 2 is upward, positive. And we can solve these for just one. If we have only two unknowns, we can solve these two equations and find these two unknowns. But if we have an elastic collision in two dimensions, then we have, in addition to the conservation of momentum, we have the conservation of energy, which gives us three equations, and that allows us to solve for three unknowns. And by this time, I am finishing this lecture, and I thank you for your attention.